Great, good afternoon. Thanks very much for inviting me. Glad to be here. So I'm going to tell you about some of the work we do with dynamic locomotion of Millibots. Our motivation here, there we are. Our motivation is eventually we want to make large swarms of very inexpensive disposable robots will be able to navigate very extreme and hazardous terrain. Now, this terrain is going to be such that the robots are probably, a lot of them are going to fail during this, and so the robots will be very cheap. And so that leads us to have very inexpensive methods of manufacture, and also the robots have low intrinsic complexity with small numbers of actuators, so they can be made very cheaply. So we're a long way away from doing so far anything as complicated as that, so I'll show you the maneuverability we're working towards in the plane. So we've got a long way to go. We've been building large range of designs of robots in our lab at Berkeley for several years. Just some pictures here to show you some of the devices we've made. We've got an interesting process for manufacture. Uses of laser cut sheets with lamination, and we can build pretty much any planar kinematic structure we want and fold it up into more complicated machines. So we can see that it's also a scalable process, so you just by changing some parameters you can build large or small robots. And one of the first ones we made back in 2008, little autonomous crawler, just shows you can, if you want to, pack everything into a very small package, about 2.5 grams. The current motor and battery and processor technology lends us to make things a little bit larger than that. So we'll be talking about things that are more on the size of a palm size. We're making some of these designs available if people want to try them out. This is OpenRoach. This one is it's made of old cardboard processing with flexure hinges. This will carry an Odroid U3, so you can run ROS and Linux and all that good stuff on it. And this is available, and I think it's a $10 gearbox and $2 of cardboard, and you just put your electronics on it. You can buy the parts from SparkFun, and you can put one of these together and get the design. We don't have all the, may require some hand holding, but if anyone's interested in putting that together, let us know. Glad to help you out. And we have the earlier designs also available. So what I want to focus on today is a variety of steering methods we've come up with. We're a little bit surprised that there still seems to be sort of a space of interesting steering modes that haven't yet been discovered. So I'll show you some of the ones that we've been working with. Very beginning, we'll just go through all these real quick in the remaining few minutes. We'll start with a very simple, conventional, let's pretend the robot is a tank and drive the two sides at different speeds. That kind of works not very well. A couple fast methods of turning using inertial tail, another fast method of turning using aerodynamic forces. So the faster the robot runs, the faster it turns. And two new methods I want to talk about. One is by coupling a roll oscillation, which will generate a yaw based on the contact forces of the feet. And then, well, even more surprising one here. These robots have two motors. I'm going to show you that we can do steering in the plane with just a single motor, where the single motor controls both forward motion and rotation. Okay, so this is from a couple of years back. You can see, hopefully it comes a little bit dim, but you can see the robot is turning and it's hitting a couple discontinuities there. It's got a controller on it to maintain heading. It's at about 90 degrees per second. Here's a discontinuity. It hits that and recovers. These feet are basically having to slip because it's doing a tank-type motion, right? So one side is going faster than the other. It means that the legs have to slip. There's only one motor driving each side, so there's no idea that the legs are performing any trajectory that changes based on how you want to steer. So if you want to turn even faster than that, here's a way to do that using an inertial tail. And you can see here this is a reduced speed. This is again a palm-sized robot, and it does a turn in 90-degree turn in a quarter of a second. So it'll turn while running, turn in place. The tail is nice because it's not so dependent on the friction of the ground. The robot will turn even on ice. And again, you can put a nice little gyro controller on there, bang control, and do fairly precise turns. So another way to turn is if you're running fast and need to generate a moment, is to put a sail on the back of your robot. So just run quickly, generates a little moment, and you can see it turns. And the nice thing about this is that most turning methods, like if you're trying to rely on wheel slip, you can turn really well if you're in place. You can turn in place very easily, but the faster you run, the harder it is to turn. Well, this is generating a turning moment, which is going to be proportional to velocity squared. So the faster you can run, the faster you can turn. And we came up with a little metric, which, you know, these metrics are usually not, they're usually kind of chosen so that your robot looks good, but it's a reasonable metric, which is the degrees per second multiplied by the meters per second, and okay, the robot looks pretty good by that metric. And you can see the control cases here. If you just put a mass on it, it's not a mass effect which is causing it to turn. It is an aerodynamic effect. Okay, so yet another way to turn. So the robot is running along. This was actually found in very serendipitous fashion from some treadmill data that Duncan and Austin had found that the robot, for some reason, with some combinations of frequency, just spontaneously did a very nice turn. And we did some analysis on it. What's going on is as the robot is running along, it's rolling like this. And so if you time the roll with the leg contact, you'll get a good rotation. So let's show you the movie. Okay, so this is the robot, and we'll do a little turning while it's warming up there. Here are the example trajectories. Find two particular phase offsets between the left and the right sides. The two sides are running at exactly the same speed, but just with a different phase offset, and that allows the robot to rotate one direction or the other. Okay. So the last thing, let's, two robots, that's too much. Sorry, two motors, that's too much. Let's just use one motor. Just make things a little more interesting to try to understand what's really going on in some of these steering things. It's an imbalance between the forward trajectory and the turning moment. So here's a very simple idea here. Make one of the legs compliant in the center, and now if you apply a trajectory so that it accelerates while that leg is in contact, there's greater load, that leg will displace more because of the compliance, causing a contact location offset, which then generates a moment compared to the legs being balanced. And let's see that, here it works. So very simple leg with compliance, and just by changing the acceleration during the time that the middle leg is in contact, you get a rotation, and you can, in the yaw plane, and you can rotate, you can get the robot to go around those obstacles. And so here's some example trajectories. So it's actually controllable with just a single motor. So there's a lot of interesting things we think from this that we want to understand what causes robots to turn, what causes robots not to turn, then put in, of course, very rough terrain and see how can you maintain a heading or take advantage of the terrain to turn if you'd like to. So to conclude, just to show you five simple methods of turning, and I think there's going to be a lot more interesting turning things, particularly as we try to run on rough terrain. So I'd like to thank all the contributors to this work, the students from our lab, Duncan and Andrew Pullen, and thank you for your attention.
I have a question. Can you say a little more about the single motor turning and to which extent you have control to kind of turn how much you like and the direction you like?
Yeah, it can turn either right or left just by changing the timing, so that the center leg will displace, will bend more or less, and so you can turn big circles, small circles, left or right.
Let's thank Ron again.